Okay. Well, thank you for the opportunity and for the introduction. It's kind of you. I'm excited to talk to you all today about something. AI and machine learning for materials started about 15 years ago, and there was a lot of hype, and there was, I think, worthy pushback on it. But I think what we've done is we've turned the corner to where it's sort of undeniably useful. And now, in the most recent year, I think it's actually igniting what I would consider a revolution. And that's a sort of over the top term, but I think it's true when you consider what it's making possible. I'm going to try and make that case today. And I'll do that by talking about two specific case studies. But first, I'm here at the University of Utah in Salt Lake City. If you've never been, I hope that you'll come and visit us. It's a beautiful place to live and work, and it's one of the most sort of rapidly rising universities in the United States by the metrics that we can sort of collect in terms of research funding, publications, citations. Utah is one of the fastest, it has the strongest economy in the United States and is one of the fastest growing states as well. So we're excited to be here and sort of represent my hometown of Salt Lake City. All right. The work I'm going to show you comes from two amazing PhD students, and it was really just my pleasure to be their advisor, and I get to, tell you about their work, but they're the ones who did it. So I want to give credit where credit's due. On the left, we have Trupti Mohanty, and on the right, we have Hassan Saeed. Both of them have just graduated the group in the last 3 months, and they're now postdocs at national labs in the United States. What are we going to talk about today? I'm going to make the case that large language models have made serious strides towards solving two of the grand challenges that we have in materials. Grand challenges, right? Things that there's no way that we can solve them without some major change in the way that we've done things. One has to do with limited data. Again, I've been in this field for long enough to know that for years we always said, material science and machine learning, it would work if only we had the data, if only we had the large data sets that our friends in crystallography or in other fields have. And I'm going to show you that I think that excuse is going away. I think that we now have data through a tool that I'm going to call Nomad, right? And then the second thing is inverse design. The thing that hooked me in this field 25 years ago when I first learned about it was this idea that if you know how the linkages work between structure, property, processing of materials, then you can work backwards. You can say, for this new application, which must have these properties, now tell me the exact material that would do it. That's inverse design. And we've been trying to achieve that for a very long time in this field. It's the sort of the dream. And again, I would argue that large language models are making that start to look like it might be possible. So that tool is called ChrisText. Let's dive into this. With materials data, it's kind of crazy to me that we say that materials should be a field with too little data, because if you look at the publications, the amount of data that is being generated in national labs, university labs, industry, it's colossal, right? This is just what gets published, which might be a tenth of the data that's actually being generated. And yet, take a look at this. The number of publications in all of these fields, and I could add more, and they probably would look the same, is something on the order of 10,000 papers per year, right? That's a log scale on the y-axis. So it's an explosion of data. It's exponential growth in the amount of data being generated. But that data has historically been trapped in these PDFs, locked behind paywalls of publishers, and not accessible for data-driven science, which is a real tragedy. Can we fix it? Um, I think my computer's stuck. Oh, there we go. Okay. Can we fix it? In the 2010s, there was a real effort to try and address this problem. We recognize, hey, there's a lot of data in the literature. Can't we just scrape it out with different tools that we build? And the tools that were built in the 2010s were well-intentioned but low performing, not good enough to actually build reliable databases that anybody wanted to use. You might have heard of some of these Chem Data Extractor, Chemical Tagger, Oscar 4. Well-intentioned but not good enough to do anything yet. As we progressed into the latter half of the 2010s, approaching the 2020s, things did get better. In fact, I remember being at the TMS meeting when the paper on the far right by Edward Kim, Olivetti and company were presenting that. And I'd already had 10 people email me that paper saying, check it out. Look at this data extraction tool. What do you think of it? And I remember sitting there in their presentation thinking, Colin, God bless them for trying, but this is just a hard problem. And this tool, while well-intentioned, is just, in my opinion, not yet good enough to really, I wouldn't build a database out of it and then use that database, is where I was at. But it wasn't for lack of trying, right? Well, if you notice the date of when that paper was submitted, you have to squint to see it. But it was what, in the summer of 20, what was it? 2017. August of 2017 is when they got this paper. Something had happened the month prior in July 2017, and that was the transformer architecture. Google's now famous paper, Attention is All You Need, had come out, and these authors obviously didn't know about that quite yet, but that completely changed the field. Transformers allowed us to build language models that are much, much better and specific to different subdomains. Like here you see Cybert, Chembert, and MatScibert. These are transformers trained increasingly on specific subsets of data so that it really understands how different fields use language. And this should make it better. The tools that we're using for data extraction should work a lot better now that we've got models that work for that specific field. That said, the paper that changed my mind didn't come out until a few years later in 2022. In December of 2022, a preprint came out from the folks over at Berkeley. This is Anubhav Jain and Berkeley, Cedar and others. Um, and essentially, they showed that you could take unstructured data. It was only in the abstract, but they could take that abstract data and using a GPT-3 model. So this is prior to ChatGPT. This is the precursor to it, GPT-3. They could structure that data. Now, it required a lot of manual examples, 100 examples just to get it even partially tuned, and then another 500 examples before it was sort of enough data that you could take unstructured data and structure it. When I saw this, I finally thought to myself, I think that the tools are now mature enough that we could probably solve this problem of getting data out of the literature and into databases. So we decided to jump in because after all, this first paper, while it was the proof of concept, it had serious problems still. For example, token size. The reason that they were only taking data from the abstract is because they didn't have the token size windows, the context windows that our modern day language models do. We're only 3 years later, and nowadays it seems silly. You can upload, dozens of PDFs. But back then they couldn't. It was abstract only. The other problem that they faced was the data in the figures. More on that in a moment. And then the most troubling one is the hand labeling. Doing 600 examples of hand labeled data is a pretty big barrier to building a data set. At that point, you've kind of built the data set in many cases. So we wanted to figure out what is the opportunity here for those of us that want to build materials data sets. And maybe the first place to start is just to take an actual reckoning, a real understanding of what does the materials data landscape look like. In other words, if you were to just explore where and what types of data materials exist in the materials literature, what would you find? Well, there's different places where you could look for materials data. Obviously in the text, right? Here's an example from a paper. It's talking about, I don't know, some sort of magnetism. There's named entities, right? The names of formulas. There's descriptions of processing. There's descriptions of characterization. And then there's actual properties reported here, all in the text. Like you will find all of those things in the text of papers. There's also tabular data in tables. This has the benefit of being partially structured, right? The whole idea is that we're trying to go from unstructured text into structured tabular data gets us most of the way there. But it doesn't have all the types of data typically that one might be looking for. Processing conditions are very irregularly reported here. Characterization is actually not super commonly reported either. It's usually named entities and properties that you find in these. And then lastly, you have figures. The richest source of data by far, tons of data here, but it's not always the data that you might care about. It might have the preliminary raw data, but what you want is the process data. Like, okay, you have X-ray XRD spectra, but each one of those data points is not what you care about. You might care about the subsequent sort of analysis of the weight fraction of the different phases in the powder diffraction sample, right? As opposed to every single data point. Overall, when we looked at this, it was kind of a disappointing picture. Here's what we found. If you look at the four different types of data, named entity, processing, characterization, properties, um, probably what you want if you're going to build a database for machine learning is named entities paired with processing conditions and performance. Characterization, maybe. And the problem is that if you look at where the data is held, figures have a vast, vast majority of the properties, and we're not going to be able to get those with our GPT-3 model that, came out in the 2020s, early 2020s. Um, I was sort of bemoaning this fact when somebody told me like, well, aren't modern day multimodal models actually able to ingest images and shouldn't they be able to get it? And I remember saying, oh yeah, but they can't do this. There's no way. Because I had seen attempts, I've been in this field for 15 years now. And back in the early 2010s when I was starting in this field, I had seen companies like Citrine Informatics try and do computer vision data ingestion and none of them worked. So I decided to come back and give it another shot. What you see on the left here is an image, I think it's an XPS spectra from some paper. And I just sent it to a series of different multimodal models. Just, these are flagship models by the companies that were available at the time. And we basically said, with no additional information, we just said extract the data points from this. And then we compared it to what a manual extraction would have been had you used something like Web Plot Digitizer or Data Thief. And to my surprise, it's actually not terrible. I mean, it's not going to be anybody who does XPS realizes that being two EVs off is like devastating. I get that. But look at the general trend that it's able to do here. It's able to capture the trend for sure. The rough orders of magnitude are all correct. The scales are more or less correct. There is some shift both in the X, Y, and if you notice, the light blue data sets also have a Y shift on their baseline. So it's not perfect, but it is way better than I expected. Because remember, these are general purpose multimodal models. These were not fine-tuned to do data extraction from figures. This was just me dropping ChatGPT and Perplexity and different tools and saying, grab that data. To my surprise, it's actually getting pretty close. So we tried this with harder tasks, like what if you give it a data set with three different data sets? This is very common in material science. You might have it as a function of different frequencies, as it is in this figure, but it could be anything else. And again, we see the same trend. It's definitely able to capture the trend. It's able to capture the data, roughly the right number of data points, roughly the right even XY values, but not perfect. Some things that I thought would be easy, it actually totally bombed on. Like, take a look at this one. This one, I thought it would be relatively easy to grab those 20 or so data points, but it was very confused. All three models were very confused by the line that's meant to be a guide for the eye from the fitting. Totally threw it off. Some things it did really well, like better than I expected. Here we're looking at semantic understanding, right? We're basically giving it a figure where a human can understand that these are steps and there's things happening in these steps. So you have to extract meaning, not necessarily quantitative data points, but meaning. Both, all the models we tried actually do a very good job at this. So you can take a look at this. It's actually no longer on ChemArchive. It's actually published in the journal Integrating Materials and Manufacturing Innovation, where I serve as editor-in-chief. Obviously, I don't edit my own papers, so we had a guest editor step in and help us with this one. I think it was Jim Warren. So thanks to him for doing that. All right. So we did decide to, now that I'm like, this is probably a solvable problem, let's actually make some real steps towards it. The first thing that we wanted to address was this problem of human labeling. I don't want to label 600 examples. Well, around the time that this had come out, Gemini was offering a slick user interface for doing structured prompts. If you're not familiar with structured prompts, it's basically you're asking the language model to do a task, but in your prompt itself, you're saying, I want you to do this thing. By the way, here's some examples. Had this been the input, this is the output I'm looking for. This does much better. Structured prompts give your language model a way for you to explain what you want the end result to look like. It can massively reduce the amount of data needed for training, is what we've seen in the past. So we tried it out here. And sure enough, you can give an example, had this been the block of text on the left, unstructured, here's how I want you to organize it. And you give an example of it structured into, say, a JSON file format on the right. So we tested this out. We tried it on 10 different papers. We did only five examples on the structured prompt. So we gave it five examples of what an input-output pair looks like. And then we repeated this process 5 times to look at the stochastic nature of language models doing this, and then compared that with five examples from human labeled individuals just to see like, is it doing what a human would do here? And the results were they were disappointing. What you're seeing here is four different metrics that tell you how good of a job it's doing at capturing the data from the text. Now, if you're not familiar with Rouge score and BERT score, basically Rouge score says, does it have the exact word used? So let's say that like the materials property was like 0.75 of whatever the units are that we care about, but it extracted 0.74 because it got it slightly off in the extraction. That would get no partial credit with a Rouge score. It would just be incorrect. A BERT score, on the other hand, would give that partial credit. Or if you're extracting text, and the actual term in the paper was precipitation, like a precipitation reaction, but it extracted co-precipitation. A BERT score would give you partial credit because those are kind of similar. A Rouge score would give you no credit. And what you see here is that BERT score is pretty good. In other words, we're getting close. We're getting like the synonyms of the data, but we're not getting the actual data very accurately. The Rouge scores are pretty low. So we were pretty bummed about this. Can we do better, right? It is a promising first start. This was published in I forget which journal we published in. I think this was in IMMI as well. How do we do better? Well, the problem is that we were using vanilla LLMs, or when we say vanilla, we mean just baseline language models that think early days of ChatGPT. And these are riddled with problems like hallucination. And even when they do hallucinate and they make a mistake, there is no validation or correction mechanism. Like it doesn't check its own work. And then critically, it also has inconsistent schema compliance. So you asked it to organize the data in a certain way, but if you run that model 5 times in a row, it will organize it in different ways. That's a real problem because if you're going to try and build a database out of it, and in one case, it called like synthesis, and the other one it called it like synthesis methods. You would have to know that those two are pointing to the same things and collapse them together. It becomes a mess. Basically, you're doing it by hand at that point. So we want to fix those problems. And fortunately, the field has evolved over the last 2 years in a way that we can now do this pretty effortlessly. 2025 was called the year of the agent. 2026 is being called the year of the personal assistant, digital assistant, and probably with good reason. Agentic workflows have really changed the way that language models offer value to us pretty dramatically. In this diagram, it sort of shows what's going on. It introduced this idea of chain of thought, where now a query comes in from the user. The LLM has a chance to think about different responses. It can decide different actions that it could take. It will actually perform those actions. So now you have an observation possible, and it will ask, did I do what I think the human was asking me to do or not? And if not, maybe you actually want to go back and try another action. That's a big deal. That allows us to find problems, fix problems, do other things because you have different actions possible. It allows for tool calling, for example. Tool calling allows us to define a schema ahead of time. Like, here's how I want my data organized in the JSON file. Now, use a tool, in this case, Pydantic, and force it so that the output of your language model matches this predefined schema of output. Works beautifully. Gets rid of all your problems of inconsistent outputs that no longer match. Um, all right, so I'm going to show you our solution for data extraction using an agentic workflow, and it has essentially solved all the problems that we're facing. First off, we have to go from paper, we have to parse the data, we have to extract the data, we have to then evaluate our extraction, manage the result of potentially multiple extractions, flag the data for the user, telling you whether it was a good or a bad extraction, and then format it finally and put it into a database. All right. So let's start with the parser. There's lots of different parsing tools. We used NuGet for a long time, neural optical understanding of academic documents from Meta. We've switched recently to Docling. I think it works a little better. It's going to take from the PDF, it's going to grab everything that's text, and it's going to separate those from tables and images. Okay. And then we actually pass the table and the images. You could pass that to something like GPT-5, a multimodal model, to turn those into Markdown language. For the papers that I'm going to show you today, we only did that with the tables, not the figures. The extraction, I already mentioned that we're using Pydantic. That allows us to enforce a very specific schema to get our JSON file format that we wanted. Now let's take a look at the actual extraction. Okay. When we do the extraction, here you see the top left is the snippet of text from the paper. It might have said like the thermal conductivity of alumina is 32.5 watts per meter Kelvin at 300 K. But what got extracted, if you look at it, it might not exactly match. Like the key values here are the value and the measurement condition. But if you look at what got extracted, maybe it made a mistake. It might have hallucinated. It might have said it was 32 instead of 32.5. It might have just ignored the measurement condition of 300 Kelvin. So it's the evaluator agent's job to actually compare the input, like what was the raw data, what was our extraction value, do these match? It asks, do they match? And it finds problems. And sure enough, it'll notice like, actually, I found a hallucination, and here's the suggested change to fix that. And actually, I found a missing condition, and here's the suggested change to fix that. And so it allows it to actually trigger a new extraction run. And critically, when it sends that new extraction, it sends the evaluator feedback to the extraction agent. And obviously, when you tell it what it messed up on the first time, the chance that it's going to do better the second time is much, much higher. And that's what we see here. We have now here's the example of multiple different extractions, and you can see that in both cases it got something wrong. Maybe it went to 32 the first time, but 33 the second time. But it did capture the measurement condition the second time. So now it's the manager agent's job to say, okay, given the possibility of multiple, we gave it up to 3 different tries of extraction. So we say there's 3 different extractions plus the original text. of all those extractions, what data is the most correct? Like which ones should we actually use? And so it's going to create this final aggregated final result. Um, and hopefully this is going to be accurate. Obviously, if you gave it more chances to do extraction, it will do continually better and better at the cost of higher language model. Okay. And then comes the flagging agent. I thought we were sort of done, but my student Hassan suggested that we add this, and it was a good suggestion. He basically says, hey, we have all these results of like how many different, what types of errors occurred, how many types of extractions did we have to do, what sort of problems did we measure? Like when it was a hallucination, how far off was it? Was it 1% off in a, a continuous variable value, or was it like 100% off? Like the idea is that you should trust a model different amounts depending on how far off and what types of mistakes it did. And you can actually quantify that trust in the extraction using this flagging agent. So you can actually come up with a score. We actually built a rubric. We defined like if it ever had to do, if there was ever a hallucination or if there was ever a missing value, right? Those were like specific values that reduced your confidence. And so the grading flagging agent used this as if you were grading a paper, and it reduced the confidence in the overall extraction. And you could sort of set thresholds that you decide are worth going back and reviewing this by hand. Like maybe you just don't trust it. Like it's just not good enough at this point. Somebody should go back and hand review this data for extraction, but at least you have this tool to do it. And in the end, now you've got this full workflow. It is agentic through and through. The catch here is that you're using, this is no longer like one LLM call like in the old days back in 2022, where you ask a language model to extract the data and just hope and pray that works. You are now being systematic. You are testing and evaluating, you are double checking your work, but that comes at a cost. You are now doing a lot of agentic calls. And so it does drive the cost up. I'll mention the cost in a moment, but let's first compare the baseline performance. What we saw before, our baseline was what we showed you before in sort of Rouge score. It was essentially 50 percentile. And that's what we see again here. In the metrics that we explored, if you don't give it the agentic process, you're looking at about 50th percentile in both precision and recall. But in this new agentic workflow, you can achieve well over 90%, which is really exciting. The cost, though, means that you're doing many calls. And in this example of this paper, we're, using flagship models, which are the most expensive. That said, the total extraction on a per paper basis, even using the very best models, and you could probably get away with cheaper models, at least for some of the steps in our agentic process, right? Like here you see like what, 5 different agents. Maybe you don't need the flagship model for all 5 of those. Um, that said, even if you use the best one, we're at about 70 cents per paper. So what do we think of that? I, I tell some people and they're like, oh, that's totally a deal breaker for me. It's way too expensive. But I don't know. I'm sort of like, gosh, like let's say like how many papers do you typically have that you want to extract data from? If somebody has like a Zotero folder with 1,000 papers in it, I'd be impressed. Like that's uncommon. If you then wanted to extract the data from all 1,000 of those papers in your folder, that's a $700 proposition. I don't know, like I'm an experimentalist. Like I've spent $700 on a single crucible before. I'm I don't think that this is a barrier anymore. I don't think that materials data is a barrier like it once was. I think we still have to collect and organize the data from literature, like find the PDFs in the first place. I think we still have to think about whether they're apples to apples comparison or whether we're not comparing things. Like there's still concerns, but getting the data out of the papers, I just don't think it's an issue anymore. I think that it's essentially a solved problem. The big thing that we have to adjust before we can fully go nuts on this is get data from figures, and that's something that our group is actively working on, is building vision language models specific to extracting data from figures, and we're very excited about that. Okay, so you can read all about it. This is published in Integrating Materials and Manufacturing Innovation, again, the journal where I'm an editor. This one we had a guest editor, I think it was John Allison, because he runs databases and data sets, and so we thought his opinion might be helpful in editing this one, so appreciate him. Okay, so we've talked about the problems with limited data, and we're hugely grateful to the National Science Foundation for supporting our efforts to fix that problem. Let's turn our attention to inverse design. Okay, with inverse design, my gosh, there's been so much talk about this lately, and with good reason. It's pretty exciting. You've seen the papers on Mattergen, you've seen the papers on genome, you've seen the papers on, there's so many, and big companies are gotten involved that it's no wonder that it's sort of in the news and got people pretty excited. But they're not exactly doing what we in the field want them to do. For one thing, they're not really doing inverse design. Matter gen gets pretty close. Matter gen allows you to have property guided generative design. So you can say, like, I want a material that has a bulk modulus of this value. That's what they showed in their paper, right? And then they showed that they were able to get within like 20% of that value in this artificial material that they generated. So it's getting there. But when I think of inverse design, I think of it in terms of how my friends in chemistry or old school material scientists might do this, where you say, like, okay, in this domain that I care about, you typically describe the crystal structure. Like let's say you're working on lithium ion batteries, right? If somebody said that they wanted to use inverse design to come up with a new electrolyte for lithium ion batteries, they'd probably say something like, well, it darn well better have lithium in the structure, and it better have channels or layers, and it would be better if the lithium was occupying a partially occupied site, and even better if that site had really big thermal displacement parameters, and if there was no hard anions. Like they could go on, they could give you like a list of description using words that really would probably be design rules that would probably allow you to do inverse design. What I think would be really slick is if we could take those descriptions and use that to guide our generative AI models. And I think it's possible. Let me show you an example. Um, First off, the field has gotten pretty excited about this. There are now dozens. This paper came out in 24. It's now 26. Like there's probably 20 more models out there. And some of these are ours, right? Chris Tent's shown with the check mark. This was our effort to work in this field. What most of these have in common is that you're using coordinates and you're using something like a diffusion model to generate new candidate materials. At least that's what many of them do. VAEs, GANs, diffusion models. There's one that really stands out as unusual, though. This paper in the middle, Crystal LLM, that used an autoregressive transformer. I was there in England on my sabbatical when this I met this team and they told me that they were going to work on this, and I was like, oh no, this is not going to work. I told them it was a terrible idea and not to do it, and I was wrong. Luis Antunes, Keith Butler, Ricardo Crespo, to their credit, came up with a really clever idea. They basically said the Civ card, which describes, if you're not familiar, it describes the shape and what's inside the unit cell for periodic crystalline matter. They're like, that's just text. So why not use a language model? That's, after all, great at interacting with text. Now, this was not a large language model that they used. It was just an autoregressive transformer. Basically, they only used the decoder portion of the model. They basically, essentially what they did is this. They would provide the first line for the phase that they wanted it to create, like K1 BR1, and then they would just let the autoregressive transformer fill out the rest of the card. So this doesn't allow for the prompting that we now get with modern LLMs because your prompt is just the first line of the code, essentially. That said, it worked pretty well. Like it has shocked everybody. If you look at the different sort of benchmark data sets for generating molecules, whether it's perovskite 5 or carbon 24 or the MP20 data set or whatever, it was competitive. In some cases, it was even slightly beating some of these big diffusion models that were paired with crystal graph neural networks that had had 5 years of a head start on them and were much more mature, I would say. And this was hanging with them even in its most initial phase. This got better as more people jumped in the field. Like here's Meta, right? The Facebook company jumping in doing this, to my surprise. They said, boy, that's interesting. What if we used a proper LLM instead of just an autoregressive transformer? Let's use an actual LLM. So they used a fine-tuned Llama 2 with 70 billion parameters. They did some funny things, like they took the Civ card and they pulled out all the information they thought mattered and they discarded the other data, which is kind of funny because language models are about understanding words in the context of other words, and here they removed all of the other words, but whatever. They've got in this like light green box in the middle, they've got the unit cell size, angles, space group, basis. The stuff that matters, they pulled out. But interestingly, and this is, I think, a key differentiation from the previous work, they used a proper language model, and so they took advantage of the prompt to do conditioning. So they basically said, we want you to create a new Civ card for this specific formula, for this specific space group, for something that has this energy above the whole. And since they were training on data where those descriptions were available, they were able to fine tune their model such that it could take these conditioning statements. Pretty cool. Their performance wasn't particularly great, right? If you look at how often it could satisfy the condition that they were prompting it with, it was like sort of less than 50% in a lot of cases. But it showed that it was possible. Now, there's lots of different ways to fine tune. They did Q-LoRa fine tuning. Basically, if you do the full-on fine tuning of a model with 70 billion parameters, then you're going to use a lot of compute. Like I don't have that here at the University of Utah. Like that is very expensive to do something like that. You would need to take over our supercomputer for a weekend to do it. Most people maybe don't want to do that. So instead, we do something simpler. We do Q-LoRa fine tuning, which is really clever. Essentially, what they do is let's say that your actual weights of your model are like 4,000 by 4,000, like a ton of them. Okay, so instead of training all of those, what if you trained two vectors that are 16 by 4,000 and 4,000 by 16, and then you multiply those together to create a something that has the same size as the weights of the model, but you're only training, a tiny fraction. Basically, you can get away with training less than 1% of the actual parameters, but you can nudge this model to behave as if it had been fully fine-tuned. It's one of the innovations that came out of CS in the last few years, and it works pretty well. So we did that, and here's what we did. We're going to start with a language model. We used open source ones, Mistral, Llama. We're going to do QLoRa fine-tuning. We're going to use data from the materials project, and we're going to explicitly explore different ways that we can use the prompt to condition the output of these models to do the things that we want them to do. So, for example, you might want it to be conditioned on the chemical formula and the space group. So, you're going to tell it exactly that. So, you give it the prompt, which basically says follow the instruction. You give it the actual instruction, which is create a sieve card. And then the input is like you're gonna obey the input that we've provided. That's our conditioning statement. Or maybe it could be about the stability of the compound. Maybe you don't care what the formula is. You just want it to be stable. Okay, so maybe that's your conditioner. You could have whatever you want here. Let's see it in action. So my student created this animation. She's reminding you what the architecture is, how we built this thing, and what are the inputs and the outputs. And then she's going to show you in action. So if you'll notice here, it's going to jump to a screen where she's going to start out by saying, okay, I want you to make a new material. The material's composition should be neodymium, silver, mercury 2 in the space group 225. And then you see in its response, it's generating the sieve card right before our very eyes. This is real time and it's pretty fast. You can generate a structure in, I don't know, 10 seconds, 15 seconds. Um, You'll notice it's already down there making the atoms and the bases. And as soon as it's done with that, we can actually dial up this structure. We could visualize it in something like Vesta or whatever. You could pass it to structure matcher and you could ask, does this match the known structure? Like, for example, if you had known what the real structure was, it would be make sense to sort of compare that generated structure with the known one and say, did it actually get it or did it come up with something totally incorrect? There's a great tool from PyMatGen called Structure Matcher that lets us do this. One of the things I like the most about Structure Matcher is that it doesn't matter what you choose as your origin. We as humans have like conventions. Like when I draw a perovskite, I always put the origin on the A atom. Like why would you put it on the B? I mean, I guess you could, but like why would you do that? The LLM doesn't know where to put the origin, and sometimes it will put it in a crazy spot. But Structure Matcher can recognize that two materials with shifted origin are the same material, which is really nice. Okay, so does it match? It it mostly does, and it's pretty amazing. Like, take a look at this. My student came and showed me this, and she was like bummed out about this is Troop D, and I was like, Troop D, hold on a minute. Look at these results. What you're seeing on the bottom right is the match rate as a function of how many times you gave it to try and match the structure. So if you only give it one try, it matches about 70% of the time. That is shocking to me. Like, think about it. You just asked a language model trained off of like the internet's nonsense, and with a very modest amount of fine tuning, via QLoRa fine tuning, it can now tell you the exact structure, like the unit cell dimensions, symmetry, and exact position of the atoms 70% of the time. That's bamboozling to my brain. Like I can't even believe that it can do that. Um, and obviously, if you give it more than one chance, give it up to 20 chances, it just gets better, right? Pretty remarkable. Now, we were exploring sort of the performance here, and we found that the performance does vary as a function of different things, like how many atoms in the unit cell. As you move towards more complex structures with 50 atoms in the unit cell, it does a lot worse than if it's only under 10 atoms. It also does better for structures where there's more examples. So class imbalance matters here. For example, space group 225, for whatever reason, nature and humans have loved to make lots of compounds in 225. So our databases are filled with examples of them. So the errors are much lower than some of the other classes where we don't have as many examples. Sometimes it will create valid structures, like it's
I have a
technically a
like,
valid structure, but it's not the actual structure. It doesn't match the known one. Take a look at that top one on the very top row, that sodium cobaltate. From my days of my PhD where I was doing experimental work, I know all about this one. It's a well-known oxide thermoelectric. But if you look at the structure here, it's swapped the positions of the sodium and the cobalt. Not going to work. Sometimes it'll look like it's getting it right, but it'll use the wrong space group, a variety of things. So these are all like valid structures, not matching structures. Sometimes it will give you invalid structures, and it can do a wide variety of things to give you an invalid structure. Take a look at this one. You have to look kind of closely. The valid structure is on the left, the invalid is on the right. And if you notice in the basis, it's put that iodine number 4 atom in terms of XYZ coordinates. It gave you a number, and a website for the Z position. So, these are language models. They can like still hallucinate, and clearly we see them doing that sometimes. Other times it'll do it more subtle problems, like it'll put two atoms on the exact same site, but it'll say that the occupancy of both of them is one. Like you can't do that. You could have partial occupancy, but you can't have over one occupancy there. Other times it will violate stoichiometry. Like it'll tell you that it matched the formula, but when you do the Wyckoff analysis, it actually did not. It'll be off. And sometimes that happens. That said, those errors are not crazy. They happen about 30% of the time. That's not great. Can we do better? I'll show you a way to fix that by the end. Um, Something that we were curious to try is we know that there's different ways to assess the validity of structures that come out of this, right? For one thing, if you know what the structure is ahead of time, you just see does it match. Well, what about structures that we're intentionally trying to use this to explore things we've never seen before? How do you know if those are valid structures? There's a couple tools that we could use, like SMACT is a slick one that came from Aaron Walsh's group and company over in Imperial College London. It's not perfect, but it basically looks at charge neutrality based off of the ions and their common oxidation states. Is it even reasonable using sort of electron counting? That helps. There's tools based off of polyelectronegativity. There's tools off of sort of normal distances. Like we know what like an average manganese oxygen bond distance looks like. So if it turns out something with like 2x that size, we probably toss that out sort of thing. Well, what you see in this plot is validity using these different tests and turning it as a function of the LLM model temperature. I don't know if people remember what this is because it's not public facing anymore. In the early days of ChatGPT, it was. There was a little box that you could select the temperature. If you remember, if you turn the temperature up on your language model, it made it give more creative responses. Turning it down took away that creativity. The way that this actually does it is it takes the tokens that the language model can choose to use, and it does a transformation on the token probability. And it essentially a higher temperature flattens the landscape. So it makes words that were probably it's never seen that word used before. All of a sudden that probability comes up and it becomes more likely that it can use that, which gives you more creative responses. What we see is that when you turn up the temperature, what do you see? The validity goes down, going from dark green to light green, dark purple to light purple. We get less valid structures, but it's not crazy less. It's a couple of percent. On the other hand, we think that turning up temperature could give us more novel structures. I'll show you that in a moment. What we're showing here is green versus gray is showing you the data that we trained from distributions and then the data generated distributions, and they match. Like if a generative model is doing its job, they should more or less match. That's sort of no-brainer. The problem is you don't want it to perfectly match. One of the big criticisms of these different generative models by people like Tony Cheatham and Ram Seshadri and Simon Billinge, and it's a totally fair criticism. They keep on saying like, yeah, these generative models are turning out structures, but these structures that they're creating are just close relatives to known structures. It reminds me of the examples that you see in sort of generative art field where, okay, you train on girl with the pearl, and then you can have it create variations of that, but it's not really new, is it? It's like slight variations. That's one of their criticisms. So we were curious to explore that. And one thing that we decided to do was use the temperature parameter as another way to explore novelty here. And sure enough, if you turn up the temperature, even though the validity went slightly down, meaning some of your structures are just not correct. If you look at it, your novelty goes up. You're able to get significantly more novel structures by using the temperature parameter, which is pretty slick. And the way that we assess novelty, I'm happy to chat about if you want to know. We have two tools that we've built. One assesses novelty based off of the chemical formula, like how unusual is that arrangement of atoms. And another one is based off of novelty of structural arrangement of atoms in three-dimensional space. We use both of those in using our novelty assessments. Okay, ultimately, if a generative model is working, then you would generate things that are realistic. One measure of realism is to actually generate the structures, and you could just have a chemist look at them, right? That's what we did for a while. A better way is to do it and then to do a DFT relaxation. Say, okay, we think these are real structures. When we relax them, do they move very much? And here's five examples where they don't move very much at all, right? Um, when our structures produced are valid, we almost always have a lowest energy structure. They don't move very much. But the problem still persisted that sometimes it would give us invalid structures. So how do we fix that? Here's an example between generated and validated here. So how do we fix these examples of invalid structures, whether it's a hallucination or whether it's, using the wrong space group or whatever else? Like, how do we fix those? Turns out reinforcement learning is a fantastic tool for this. You know, Reinforcement learning was sort of the dark horse in our field. In the first 5 years of this sort of taking off, I remember teaching a class. I've taught it now for 5 years, materials informatics here at the University of Utah, and I would talk about supervised learning, unsupervised learning, all these different things. And when I got to reinforcement learning, I didn't even have any examples of how it was being used for material science back then. And now, gosh, it's everywhere. It might be the best of all the different machine learning techniques is reinforcement learning. Here we're going to use that. In a typical reinforcement learning loop, you have to have an agent, action, environment, state, and a reward. What that translates to for us is we're going to use Chris text as our agent. For our action, it's going to be the generation of structures. For the environment, that's going to be our structure evaluator. And then the prompt and the structure becomes the state. So what we need to define is simply the reward. So let's look at some options. The way that we're going to do this is using the GRPO framework. GRPO stands for Group Relative Policy Optimization. The keyword there is group and relative. What we're going to ask our model to do, Chris text, is generate structures. But instead of doing them one at a time, we're going to look at batches. We're going to say generate, I don't know, 10 structures at a time or 20 structures at a time. And then we're going to say, all right, of these 20 or X number of structures generated, let's let's compare them relative to one another using a custom reward function that we can write. So did it pass check sieve? Did it pass structure matcher? What was the smacked score? What was, you could throw whatever we want at it in terms of goodness, right? Were there hallucinations, right? You can come up with a custom reward function that encourages it to do exactly what you want it to do and discourages behavior that you don't like. If you're not familiar with this type of rewards, essentially the catch is that, okay, you produced 20, let's say, structures at a time. If that group of 20 structures that were generated just happened to be kind of a crazy group, you don't want to completely redefine the way that your Chris text model was working. So we typically use what's called a KL divergence term. And essentially, all this does is it has two terms and it says make adjustments to the model performance, but don't make changes that would completely disrupt it. It basically says make modest changes. And then you have to obviously come up with your own rewards. We decided to come up with rewards that included a gradient. So when it says, we didn't just say like, did it pass structure match? Or we said, how closely did it match? And if it matched it really closely, we gave it more of a reward than if it only matched it, say, a little bit. What we found is by doing this is we got dramatic improvement. Yes, we got improvement in the match rate. That's what I'm showing you here. Here you're seeing the comparisons of Chris Text RL, that's our reinforcement learning in blue. And yes, it is the best performing model. It's doing a really good job with high sort of match rates. It's outperforming the models that don't have reinforcement learning. But where we really see improvement is in the invalidity rate. Remember, our invalid structures were something like 30% of the time. That drops almost to zero when you include reinforcement learning. That's able to very effectively curb our invalid response rate, which has been really exciting. So I'm at my time. I'm going to stop here and just say that this paper was also published in Integrating Materials Manufacturing Innovation. You can see that I'm a fan of my own journal. And once again, we did not do our own editing. This one, the guest editor was Raimundo Areve, so we're thankful to him for doing that. And you can check it out yourself. You can start generating structures using your own custom prompts to explore ways to make generative models actually do things that look a lot like inverse design. We're not done yet, but we're making real strides. So that said, I'll just end by reminding people if you do work in these areas that I've been talking about, I hope you'll consider our journal. It is not just a done by publishers. It's done by a professional society. It's in conjunction with the TMS Professional Society, which means it's for the people by the people sort of thing. We have a good impact factor, and we publish everything from data to tools to research and reviews. And then critically, I do something which I don't know any other journal is doing. I create these editor summary videos. every paper that gets published in my journal, I offer the authors, they don't have to accept, but I offer them the option of me creating a brief, 5-minute video where I describe the work. What was their main idea? What was their approach? What did they actually learn? And I post these to my popular YouTube channel, which you can sort of see here. And the idea is that a lo much larger audience is actually seeing the papers than if you were to publish it in a journal that doesn't do this. So far, what we're finding is that papers published with these editor videos, summary videos, are getting increased downloads. We don't know yet about citations, it's too early to tell, but they're getting much higher downloads. In fact, they look like papers that are published open access. Normally, open access gives you like a 2x multiplier in downloads, and we're seeing the same effect, but without the open access, which is pretty exciting. Okay, I'll wrap up here, and I'm happy to take any questions. I appreciate the opportunity to teach you all today. I think that we are in the middle of a large language model revolution in materials, and it's just a really exciting time to be in this field.
Thank you, Taylor, for this very impressive presentation. Are there questions from the audience? Let me see whether everyone, okay. So then,
Yes, I have one.
yeah.
So Sina Machel was impressive. And by the way, I just saw this morning, had a look to your papers and saw this video. Perfect. You said in this video that your Nomad is an open source and you can find it under GitHub. Is that
That's
correct?
right. Yeah, I can
And
put the link if you'd like.
and how about Chris text?
Yep, everything we do is open source. I'll put the links right now.
Wow. And maybe one
Um,
question. You have not mentioned Claude from Anthropic. Are you also experienced with Anthropic? Because I heard that at the moment Anthropic is Opus 4.8, even a little bit better than ChatGPT 5.5. So maybe,
I was like an open AI guy just because that's what the first one I used, and so I haven't made the jump to Claude, but all my students have.
okay,
They're all telling me that it's better, and so maybe it's time that I jump ship and join them.
okay.
Cool. Any other question or comments? I have actually a few. So then like regarding this information extraction from the literature, Taylor, you mentioned this schema enforced generation or extraction. So then my question would be, do you think, like such ontology could be helpful in a way?
Mm. Yes, actually at IMMI, I've been the editor for several submissions that have been talking about this. Like, okay, now that we can enforce the schema, what schema should we use?
Mhm.
I I am open to the fact that there might be a best option, but I'm not as worried about it as some authors are. And the reason why is because what LLMs are very good at is essentially being universal translators between schemas. So
Mhm.
I'm sort of the opinion, capture all the data. Capture all the data that you think could be useful, and we will use LLMs to be the inner, interpretation between different data schema formats that we ultimately choose. And if, Germany with Nomad, for example, wants to have a specific schema that they decide is great, and if the United States MDF, and if private companies like Citrine have their own format, I'm
Mhm.
not so worried now because now we can easily interoperate between them by using these LMs as translation agents, essentially.
Mhm.
That said, there probably are like some ontologies that are more fundamentally make sense. There's probably not a single ontology that works best for all applications, though. Like if you're a person who wants to understand new mechanisms, then you might care about a different ontology than somebody that is just interested in, raw materials discovery capability.
Mhm.
So I don't think that there's one necessarily that's best, and I'm not like I'm happy people are working on this. I don't know if it's a high priority area for me to sort of explore.
I see. Yeah, because my take on this point is, like if we know exactly what kind of information we are going to extract, we can definitely define such kind of schemas. But then if we are interested at the general extraction, like, for instance, for a piece of paper, we want to get not only the measure the property, but also the synthesized routes and also the simulation approaches and so on, like,
Yeah.
get basically all the information extracted from one paper. So maybe then I was thinking, with a properly defined ontology, we can try to get this done from as a, in a batch mode. But of course, on the other hand, I do agree that, maybe part by part would be also valuable.
Yeah, that makes sense to me.
Mhm. Yeah. So then in this regard, regarding the benchmarking of the extraction, do you think still hand labeling is necessary, or is there a way for us to skip this?
Um, well, let me say this, like I think first off, there's data sets, just like we saw the creation of benchmark data sets for everything. We
Mhm.
have like MapBench, we have Lamat Gen Bench, like for generative models. Now, the last thing I saw is that there's been a benchmark data set created for data extraction. I think Ben Blazik and MDF created that, and I have posted, I forget the name of it. I'm hopeful that there's sort of enough examples of hand-labeled extraction to train models on, and that's no longer the limiting thing anymore for models. Instead, I think it's going to be clever model architectures, maybe clever agentic workflows for correcting it. And again, my view where we're at sort of 90% accuracy, okay, I want 100% accuracy for sure, but I think 90% is good enough to actually start doing something with it. So
Mhm.
I'm less concerned about like improvements in the actual precision and recall. I think they're sort of good enough. What I am interested in is bringing the cost of these models down, figuring out, okay, is there a cheaper open source model or something that can do the same thing at a lower cost or faster? That is still, I think, important. 70%, 70 cents per paper to those on this call, maybe that's not a big deal. But I was in India,
Mhm.
and I said that at one of the IIT schools, and I was like, hey, it's only 70 cents per paper. And they're like, sir, like that could be like a big chunk of our budget. Like, when you talk about doing $700 for a data set, they're like, that's not nothing for us. And
Mhm.
I recognize that. So I am interested in seeing, can we get similar model performance, but with way less expensive or faster models? Yeah, I do want to see that happen.
Mhm. But then, like in this regard, talking about the token prices, you can then try to, kind of get such open source code, large language models allocated on site and then try to generate this. Uh, have you tried? So then I'm more concerned about the speed or how can one then try to really get a more or faster token generation with proper hardware setup. So what is your kind of take on this one?
We haven't fully explored that.
Mm,
I've had people ask that question. We used flagship models for this paper because we just wanted to know ultimately what is it capable of? Because again, I came at it with a skeptical viewpoint, like, is this really going to do it? And
mhm,
so I didn't want to give it any excuses like, oh, had we used the flagship, imagine how how good it could have been. So instead, we used the flagship model. Now it's time to sort of go back and say, all right, with locally deployed, how does it impact speed? What about memory utilization? Like, that sort of, I have one student working on that sort of, it's sort of a less exciting follow-up study, but it's important, and we'll have that ready to publish soon.
mhm. Yeah, because like I'm following the moonshots videos and so on, then they see okay the difference for the frontier large language models and the open source large language models. If you are marrying this in terms of time, they might be a 3 months delay or difference.
Yeah,
So I thought,
yeah,
okay, if then the performance is so comparable, then maybe then for those people who really want to deal with a big chunk of data or documents, then the local employment of the such open source code or models could be an option, right?
yeah. No, you're absolutely right.
Okay, good. So, I'm particularly inspired by the last part you have talked about, basically using the reinforcement learning to enhance the performance of the large language model generation. So, have you tried actually to get the physical properties as a reward encoded and then try to do something there?
Yes. The catch is anytime that you use something as the reward, you have to have a way of generating those relatively quickly, right? The way that this training works is it's just like training a neural network where there's like epochs and you might have to do hundreds. Same thing with these reinforcement learning additions to your model. You might need hundreds of rounds. And so if each one of those rounds takes a day or a week because you're doing a slow DFT calculation, that's not useful.
Mhm,
But if you can rely on a quick MLIP, instead of a slow DFT, you can do a really quick approximation. If
mhm,
it's close enough to still be useful, now you've got the ability to do rewards like that in the loop. If you're talking about physical experiments, like you're going to say, hey, I'm actually going to like make this material and measure this physical property. Like I just don't think that works because making a material is a sometimes month-long process.
mhm,
Measuring its properties can be additional weeks. That's never going to pair with this sort of reinforcement learning strategy. Technically, yes, it does. Like in principle, yes. In
Hmm.
practice, that becomes a very slow process. So I don't think that's the future. I
Hmm.
think we're going to be using these lower fidelity surrogates for the things that we actually care about as our rewards in our reinforcement learning. I could be wrong on that. Maybe clever, I'm in the self-driving lab world. I'm seeing really cool things happening there. So maybe I'll be proven wrong. But right now, I don't think that the reward in most cases will be a physical experiment. I'd love it if we could come up with a way to do that. I just don't see many ways that iterate
Hmm.
fast enough.
Hmm. Yeah, I'm thinking actually after hearing your idea about combining reinforcement learning with then the large language model generation, I'm thinking about actually using, so many established vertical models, starting from crystal structure to predict directly the properties, and then such kind of a surrogate model as a revert function. And then, like then in this regard, maybe then we can not only try to optimize the structure itself, but also the properties there, right?
Yeah,
Like thermal conductivity, superconductivity,
that's right.
whatever, there can be interesting to try.
Yep, absolutely.
Yo, good. Okay, so then any other questions, comments popping up? I think in the chat, I do not see any. I guess that's it. So Taylor, thanks again for coming.
It was such a pleasure. If
Yeah.
anybody has questions, I'm an easy person to get in touch with. I'll drop my email address in the chat here below, and feel free to reach out if you want to try one of these models out. We'd love it. Everything we build is open source, and if there's something that would make it easier to deploy it, we're happy to help out.
I will definitely get a master student trying with this large language model generation.
Awesome.
Yeah,
Okay, lovely to chat with you all. We'll be in
good.
touch soon.
You have a nice day.
Thank you.
I was
Bye
very
bye.
much impressed. Thank you very much.
Yo.
Nice to meet y'all.